Yes. Bye bye. Thanks. Hi everyone. I've sent the problem set on announcement in Discord. You can write the problem number on the chat, like which one you want to discuss first, and we can go according to that. Like, discuss or like solve. Like it will be more like a group solve. So yeah. Okay, someone has written five. I will wait. I will wait till 7:06 and then we will start. Okay, that's it. Seems like many people. Yeah, maybe let's just wait one more minute. So, yeah.
In problem number two, what do you mean by reflection of integer?
If you want to reflect an integer n about r, then like it will, where will it go? It will go to a point such that r is the arithmetic mean of n and that reflected point. So basically,
Oh, okay, I got it.
yeah.
Can you please repeat?
Like if you are reflecting a number about r, so that number will go to the point such that r is the arithmetic mean of that number and the reflected point. Like how you do usual reflection. So like let's start with P5. I think that has the majority. I will just screenshot. Uh,
Do you know the solution of these problems?
Yes, I know the solutions of this problem. So like it will be more like you guys will be like giving ideas and like I will try to guide you to the solution.
Okay. Could you please copy paste the problem here?
Wait, I'm not like I'm not sure how to do that. So
Which problem are we doing now?
problem five. So like I think you can open it in the PDF and like use the same terminology as in that.
Okay.
I'm not like I don't know how to copy paste. Yeah, so like someone asked about that reflection thing in Python. I will just like clarify it. So reflection means that like uh, if this is your point r and you want to reflect this integer n, then it will go to, where will it go? 2r minus n. So r is the arithmetic mean of these two things. Okay. Yeah, so like do you guys have any ideas for P5? Let's start with that. So basically it was that uh, so the so you had integers, uh, so integers n and p, where p is an odd prime, and 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 tk were the number of permutations of 1 to n, uh, which had number of transpositions congruent to k modulo p, right? And this was for 1 k is equals to 1 to p minus 1. 0 was not included over here. And wanted to find all n for which t1 equals t2 equals tp minus 1. Right. This was a problem. So, like, any ideas? Yes. Hello, am I audible? Like, I just want to show.
Yeah.
Okay. Fine. Yeah. Maybe you guys can like try it for 5 more minutes, and then I can maybe give some hint or some. And like those who have already like solved this problem, they can try the other ones. The problem statement is clear to everyone, right? If you have any doubt in the problem statement, then you can ask.
Can you just explain what is a transposition?
Yeah, so like suppose, right? So suppose like you have the permutation, let's say 3, 2, 4, and 1, right? This is a permutation of 1, 2, 3, 4. So a transposition is any pair like which is inverted in the permutation. So like if you will look at 3, 2, this is a transposition because 3 is coming before 2 in the permutation. If you will look at 3, 4, that is not a transposition, but 3, 4 is 3, 1 is again a transposition. And again, so if you look at 2, 4, this is not a transposition, but this is a transposition. So, and again, but 4, 1 is again a transposition. So in all, you have 4 transpositions for this permutation. So that's how. So it's basically the number of pairs ij which appear in the opposite order in the permutation.
One idea
So-
is that
Yes, go on.
I think T1 will be n minus 1, and then we can work out some details. I think.
P1 will be n minus 1.
Yes.
No, I mean like you are considering all the permutations, no? P1 will be n minus 1. So I didn't get what you're trying to say.
So T1.
Oh, okay, T1. Oh, okay. So number of permutations with only one transposition will be n minus 1.
no one transformation, p plus one transformation, we have to consider everything.
Yeah. That makes sense. So,
What we can think is that if we interchange it to adjacent numbers, then the number of transposition either increases or decreases by 1. So this might help to establish something between T1 and T2, or maybe T1, T2, T3.
yes. Yeah. So, yes. So, like, to set up the notation, like, we can, let's say, like, T of n comma k is the number of permutations of 1 to n with k transpositions, right? The t1, like the small t's were like the small t's were like the sum of all, like small t's were the sum of all like sum of the number of permutations with transpositions modulo p. So like t of something like t of s will be something like t of n comma s plus t of n comma p plus s, that way, plus t of n comma p plus 2, 2p plus s, and so on, right? So you are saying that capital T of n comma 1 is n minus 1. Hello.
No, it's not n minus 1. I just realized. I don't think so. It's correct.
Yeah. Or like if you also like the idea of like making a recursion
Also,
in
I have one request.
yeah.
Instead of having, can you move to the next slide, like so that we can access the Jamboard later?
Oh, okay. Sure. I will do it. Yeah. Okay. Yeah. Got it. Yeah. Fine. I will do that from. Yeah.
Yeah, like could you send the link of the Jamboard if possible?
Yeah. Okay. Copy link and here. It's that. Yeah. Send.
You also have to give access to us.
Okay. Oh wait. So how to do it? There's no
Click on
option
the
over
share
here.
button in the top. No, click on the share button on the top.
Yeah. And
Now, like there will be link sharing something.
wait, children who has access.
Yeah. Now click on this change link settings. Editor. Viewer. I mean.
Okay. Edit.
Yeah.
Click on editor also, please, if you want to write something then.
Yeah. Click on editor.
Now
You
copy
guys-
link and then.
okay.
Then you have to send this.
Yeah, it's fine now. Fine. Perfect.
Okay. Cool. Yeah. Okay, so someone mentioned about like recurrences, making some recurrence relation among the T's, and that was actually a nice idea. So you can take this capital T of n comma k, and also like for convenience, like we extend this definition to like k over all the integers k. So like T of n comma minus 1 is 0 because there obviously no permutations with 0 minus 1 transpositions and so on, right? Yeah. So like you can like if it so try to find some recurrence relation for Tn comma k in terms of like smaller values of n if you can.
I think smaller values of k maybe.
Yeah, like smaller values of both n and k, like basically like in terms like try to like reduce this in smaller values of n and k. Like that's one of the main ideas. Like first to find out this capital T. Is like Tnk is the number of permutations of this set with k transpositions. Oh, one definition of a transposition. Uh, Please tell what. Oh, the definition of a transposition. Okay, so suppose you have a permutation of, let's say, 1 2 3 4, and that permutation is let's say 4 2 1 and 3, right? And you have to find out the number of transpositions in this. So like a transposition basically like any pair of numbers whose order gets interchanged. So 4 2 is a transposition, 4 1 is a transposition, 4 3 is a transposition, 2 1 is a transposition, uh, 2 3 is not a transposition, right? Because 2 and 3 are appearing in the correct order. 1 3 is a transposition. So how many transpositions do you have in total in this permutation? Like 1 2 3 4 and 5. Yeah, 5. Wait, sorry, did I miss one? I think I have 4, right?
So do you mean descents?
What?
I think the standard term for this is descents.
Descents. Yeah, descents. No. Like descents are different, right? Descents are like wherever local maxima or something. Like these are the number of transpositions. Like this, what is like this can
The idea is similar, right?
like so the number of transpositions in this permutation is 6, like because every pair is interchanged. So like the number of transpositions can become like even n choose 2. Descents are like the points at which you have something like this or right. Like, did you get what transpositions are? Basically, like the number of pairs I, j whose order
Yeah, I
gets
got it.
in the permutation. So I will give you a hint for.
Is t of k comma I equal to t of k comma I minus 1? And like there are I minus 1, and then we can add 1, no?
Wait, t of k comma I is equals to
Uh,
t of.
the t of k comma I is the number of permutation with I, that
Yeah,
transpositions,
number
right?
of permutations of k elements with I transpositions. Yes.
Okay, so like now we have taken permutation with I minus 1 transposition, and then like in any permutation, if we just change the order of one pair, we get a one permutation with I transposes, right?
Like it can either increase or decrease the also like one pair must be consecutive. If you change the position of far away elements, it can like
Yeah, I
change
mean
the.
consecutive. Yeah, only
Yeah, so if
consecutive
you
one.
change consecutive elements, then it can either increase it by 1 or decrease it by 1. Yes, that's true.
Yeah.
So
So like I think it will be a linear recurrence. I mean by linear I mean like if we consider t of k comma I minus 1, it will have coefficient 1 only. I think so.
but like this is obviously not true, right?
Yeah,
Because
this is not true, but like I
uh,
think when we form the recurrence, it will be having one coefficient only. Like if we
oh
take
yeah, like obviously like you won't get like square terms and all in the recurrence. Yeah, it will be linear. Yeah. Like, yeah, but like linear and like obviously like you will have both the variables will be. Okay, so like, I can give you an idea for constructing the recurrence. So suppose like you are considering p of n comma k, and like so like what will be the number of so like suppose you are considering the permutations of 1 to n, and so like consider
I have
permutation
got an
starting with
idea.
yeah, sure.
So basically, if we switch like I comma like I and j are two conjunctive elements in the permutation. Okay.
Sure.
So now if we switch I and j, like
Yeah.
it will be changed to j comma I. Then
Yes.
if I is greater than j, then the number of transposes decreases, and if
Yeah.
I is less than j, then number of transposes increases. So like basically
Sure.
in a permutation we have to count ki after like so basically in a permutation we have to increase the transpose so we can count like how many conjugative I less than j pairs are there, like number of
But like
conjugative
the
pairs.
number of transpositions like will depend on how the permutation is globally as well, right? Like there can be pairs which are very far away but still be in the opposite order. So
Yeah,
also like I don't
I
see
mean
any
like
clear way to
we will
proceed
consider
from
the
this.
conjugative pairs, like like if I refer the by index. So at 1 comma 2 and then 2 comma 3, like consecutive pairs we will only consider, no?
Yes, but like, how would you convert that into a recurrence? Like, because like you have no control on the consecutive play, they can be anything. So,
Yeah.
okay, so like this was an idea which I had when I solved it. So
Is t of
uh,
n comma k t of n minus 1 comma k plus t of n minus 1 comma
yes,
k
yes,
minus 1 and
yeah,
so
yeah,
on up
yeah.
to t of n
Yes, yes,
minus
yes,
1
yeah,
k minus 1 plus 1.
yeah.
We have
That's
to
the yeah,
focus
that's
on
the
positions of n.
yeah, 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 yeah. Even that works. Yeah, yeah, yeah. So, yes, that's the correct idea. So,
I didn't get the recurrence what he said.
okay, I will explain it. Uh, so basically, like consider like permutations of 1 to n, and like consider the permutations which start with 1. Consider permutations which start with 2, and so on. Consider the permutations which start with n. Right. So if 1 is in the starting position, so that doesn't contribute anything to the transpositions at all, because like 1 is before every number as it should be. So the number of like you will have to arrange these numbers with k transpositions to get a permutation with k transpositions over here. So the number of ways to do this are t of n minus 1 comma k. Now, if you have a 2 in the beginning, that gives you exactly one transposition, because it is in the wrong order only with respect to 1, and 1 is coming in the front. So over here, like you will need to arrange this to give you exactly k minus 1 transposition. So this is t of n minus 1 comma k minus 1, and so on. And if you go till n, this will be t of n minus 1 comma k minus n minus 1. Right. Did you get this?
Got it.
Very good. Yeah. Nice. So yeah, we have our recurrence. Where is it not going for? Okay, I'll just put this one. Okay, so we have our recurrence, right, for the capital T of n comma k. T of n comma k is equals to T of n minus 1 comma k plus T of n minus 1 comma k minus n minus 1, right?
So the crux was to look at the first element.
What?
So the crux
Oh,
was to look at the first element of the permutation.
yeah, yeah. Basically, you're looking at the first element of the permutation to find out this recurrence. Yes.
Okay.
Right. So, very good. Now we have this. And so now, like using this, like you can easily show that why, suppose you have that statement, like let's say you
Wouldn't
have,
there be some extra constant plus n bracket min minus 1 by 2?
why, like derive this now over here. Like when you have 1 in the starting, then there are exactly these many permutations with k transpositions. When you have 2 in the starting, there are exactly these many. So on, when you have n in the start, there are exactly these many. Only
Oh
one of
yeah,
these many.
sorry.
And yeah, right. So yeah, we got this. And now, like now, so if you see the problem, you have to show this for p less than equals to n, right? So like take the first case, like when p is equal to n. So now, like okay, so like we'll do this in a sort of a diagram thing. Okay, wait. Yes. Hmm. So this thing is there. Okay, yeah, fine. So like you can say that if p is n, so how do I explain this? Okay, fine. So like using this, try to prove that using. I don't know. Yeah, so using this, like just try to show it for p is equals to n. Like this is immediate using this identity. Try to show the problem for p equals n. Like y is t1 equals t2 is equals to p minus 1, like why the number of permutations of 1 to p which have modulo 1 transpositions equal to the number of transpositions of 1 to p which have modulo 2 transpositions and so on. Like using this, it's like immediate. If you want, I can give a hint.
How immediate?
Okay, fine. So look at it this way. So suppose you're trying to find, let's say, some tk, like, right? So this tk will be like sum over j t of n comma pj plus k, right? Like, because you have to cover all the possible transposition or all the possible modulo k number of transpositions, right? Does this thing make sense?
Yeah.
Yeah, n is basically p, so like, yeah, so yeah, and now right, so now just expand this using this thing and see what you get. Like you will get like t of p and this is some of our j integers, right? So let's see what we get. Yeah, so tk is equals to sum over j integers t of p comma pj plus k, right? And so what is this thing? Like by our previous lemma, this is just t of p minus 1 comma pj plus k plus t of p minus 1 comma pj plus k minus 1 and so on till t of p minus 1 comma pj plus k minus p minus 1, right? From a previous lemma, and you have to sum this over all integers j. So like this is basically like this is basically the sum over all integers as t of p minus 1 comma s, right? Because like for every pj plus k, this is like where what is this thing? Like this thing is just p minus 1 j plus k plus 1, right? P
Let
minus
me
1.
think just a second.
Yeah. And this thing is independent of k. If you want to visualize it, like do it something like this. So let's say you make a let's say like this is your
Yeah, I got it. Basically,
Got it.
it covers every number modulo p, right?
yeah, exactly. It covers like everything modulo p, and like since you're summing over all integers, you get sum over the all the all the blocks from p minus 1 j plus k plus 1 to pj plus k, and that is basically sum over all integers, which is independent of k, right? And even visualize this by like drawing all the t and k things below each other, right?
I think we can also create some bijection between like T1 and T3
T1 and T3.
by changing the first number of the permutation.
Yeah, that is not required. Like this recurrence is sufficient to solve the problem. Okay,
Can
so
you
like
show the previous slide once? I have a
yeah,
doubt.
yeah.
But like, okay, n equal to p is here. So, how is like this covering all those numbers?
Okay, so like look at it this way. So uh, so like you have this sum now. Okay, right. So you have sum over j t of p minus 1 pj plus k, right?
Yes.
Plus t of p minus 1 pj plus k minus 1 and so on plus t of p minus 1 pj plus k minus p minus 1, so which is basically p minus 1 j plus k plus 1, right? This is what you have, right? Now like So
Oh,
the
okay, I got it.
consider all the got it right. So this
Yeah.
is like from p minus 1 j plus k plus 1 to
And J
pj
is such
plus
that
k.
like from 1 to such that
J is
pj is
over
less than
all
n.
integers. Like since we were like we like for notation convention like we will say that t of n comma minus 1 is 0 and t of n comma minus 2 is 0 and so on. Like so, only finite number of terms are non-zero in this. Like j is over all integers. So
But
you
how does
get
all
a sum
integers
over
make sense?
so I am declaring these things to be zero. Now t of n comma minus 1 is 0, t of n comma. So only a finite number of terms will be non-zero in this sum. This is basically for notational
Yeah,
convenience. Like
like what about t comma p plus 1? Okay, just take
yeah,
t comma.
yeah, yeah. So if p has some number of permutations with if you're saying p choose 2 plus 1, right? Even that is zero. Those things won't matter. Like whatever. Like if you're
Okay,
exceeding the limits,
great,
then
great.
a is automatically
Okay,
zero.
okay. Got it.
Yeah. Yeah, so now we have shown we have shown that T1 is equals to T2 is equals to Tp minus 1 for n is equals to p, right? In fact, we have shown this even for T0. Like over here, like it did not matter like whether I chose K0 or not, right? This thing covered sum over all Tp minus 1 comma SC1 then,
Yes.
right? Nice. So now once you're done with this and you have this recurrence in your hand, t of n comma k is equals to t of n minus 1 comma k plus t of n minus 1 comma k minus 1 plus t of n minus 1 comma k minus n minus 1, right? So now you have this thing and you have this recurrence in your hand. So like using this, you can easily show that if it's true, if t of t of k is, and it's like writing n in the subscript to show that it is for permutations of 1 to n. If this is independent of k, then this is also independent of k. You can easily show like by induction and using this formula, because you will just get that this is, you can just shift all the residue classes behind by uh, using this, and the sum will correspond, like all of them were equal for the n case. So does this make sense? Like why does this all are equal? Also, like I'm assuming that t of n comma 0 is equals to t of n comma 1 is equals to t of n comma p minus 1, and this implies this like,
Yeah, yeah,
but
just induction.
yeah, it's this induction, like like it's wait, what happened? Yeah. Am I audible?
Yes.
Okay, sure. Yeah, so we are done with one part of the problem, like showing that t1 is equals to t2 is equals to tp minus 1 for like n greater than equal to p, right? We are done with this part, uh, right? You already showed it for n equals to p, and then you showed that.
Yeah.
Yes, nice. Now the second part is like much more interesting than this one. Like it's also somewhat non-trivial. So like I can give you just like 5 minutes to think about that. Like why should it not hold for n less than p? Like why should it not hold for n less than p? That t1 is equals to t2 is equals to tp minus 1. Okay, fine. So I will give you a hint. Uh, so like suppose you have t. So like the main idea in this to like do some sort of a backward induction that if tn1 is equals to tn2 is equals to tn p minus 1 holds true for some n less than p, then t of n minus 1 comma 1 is equals to t of n minus 1 comma 2 is equals to t of n minus 1 comma uh, p minus 1 will also hold true, and so on. So but we already know that like you can't keep on doing this forever because t of 1 comma 1 is because like t of 1 comma 1 is not equal to t of 1 comma 2 because like the set 1 like has zero transpositions. So like, so t of 2 comma 1 is not equal to let's say t of 2 comma 2 whatever, like for small values this thing does not hold. So try to go from here to here using this uh, using this inequality.
How to like decrease the value of n, like increasing can be done by direct induction, but we have not yet find a recurrence for n to n minus 1.
Yes, like that's the like so I give you a hint. So like you know this thing, right? So like what is the way to go from n to n minus 1? So try to think that if I give you t of n comma k plus 1, right? And if you like take the difference of these two things, so like most of the things over here will cancel, and you will be only left with two terms like t of n minus 1 comma k plus 1 minus t of minus this thing t of n minus 1 comma k minus n minus 1, right? And if you will sum it over all such k's which are congruent to this k modulo p, you can like you can get like something from this small t's also. Does that make sense? Like
Yeah, seems very logical.
yeah, yeah. This thing makes sense, right? By using the
Yeah.
Now, suppose you know that t of n comma 1 is equals to t of n comma 2 is equals to t of n comma p minus 1, right? So, obviously, if you will sum this over all such numbers congruent to k plus 1 modulo p and k modulo p, so you can basically show that t of n comma k is equals to t of n comma k plus 1 implies t of n minus small t of n minus 1 comma k plus 1 is equals to small t of n minus 1 comma k minus n minus 1.
Let me think about this. I'm not 100% sure.
Just basically sum this over all j t of n comma pj plus k. Sum both these sides by introducing pj plus k plus 1 pj plus k pj plus k plus 1 pj plus k minus n minus 1.
Can you show that the 10th slide only?
Oh, yes.
Can you tell you did first line thing that became equal? After that, what did you do? I couldn't understand that.
Okay, so right, so this thing you understood by capital T of n comma k
Yeah.
plus So now if you okay, so now basically what you do is that you do this thing. Okay, I will move on to the next slide. Right. So try to see what this thing is. Sum over j capital T of n comma pj plus k plus 1 minus capital T of n comma pj plus k. Right. So from what we proved, this is basically sum over j of t of n minus 1 comma pj plus k plus 1 minus capital T of n minus 1 comma pj plus k minus n minus 1, because of this k minus n minus 1 coming here, right?
Yeah, I got
basically
the claim you made here. Like I got this below written thing on slide 10.
yeah, right. So yes, so now what was this thing? This thing was just small t of and so suppose that small t of n comma k plus 1 is equal to small t of n comma k. So that means that this sum is 0, right? Which must also mean that this sum is 0, which must mean that small t of n minus 1 comma k plus 1 is equal to small t of n minus 1 comma k minus n plus 1, right?
Yeah.
Yeah, I got this, right?
Could you repeat?
Yeah, so this thing you understood, right?
Yeah.
Yeah. So and now what is this thing like? What is the first term over there? Sum over j of this thing. This thing is just small t of n comma k plus 1, right? This is the
Yeah, I
sum
got this thing you have written down.
Yeah. So we got this thing, right? And now what I'd assume was that let's say for some n less than p, we have t1 is equals to t2 is equals to t of n1 is equals to t of n2 is equals to t of n p minus 1, right? Remember that t of n comma 0 is not given to us over here. Otherwise, we can easily go below with this step, right? So what will this give us is that it will give us some various inequality. First one will give us that t of n minus 1 comma 2 is equals to t of n minus 1 comma k minus n minus 1. So 1 minus 1 minus n minus 1, obviously this is modulo p and all. So and then t of n comma 2 is equal to t of n comma 3 will give us that okay, so t of, maybe let's just do an example. So
Basically, t of k is equal to t of k minus n.
Yeah, t of k is equals to t of k minus n for so t of k is equals to t of k minus n. Yes, that's true. T of k is equals to t of k minus n for k from 2 to p, right? K is equals to 2 to p. Think so, hopefully. Yeah. This like because k plus 1 over here starts like k starts from 1, so k plus 1 starts from 2, so that's why, right? Hello.
Could you repeat?
So you get so assuming that this thing is true, second, right? So assuming that this thing is true, that t of n comma 1 is equals to t of n small t n 2 is equals to small t of n comma p minus 1, you so once so you had that t of n comma k is equal to t of n comma k plus 1 implies t of n minus 1 comma k plus 1 is equals to t of n minus 1 comma k. This is what is this? This is basically,
Yeah, this is clear.
yeah, k plus 1 minus n, right? So from this, you will get that t of k is equals to t of k minus n. This is both a modulo p, obviously, is for all k is equals to 2, 3, dot p, right?
Why
This
not
is
k equal to 1 even?
because like this thing is starting from 1, so and over here we had k plus 1, right? If this thing was if this series of equalities was starting from 0, then we could have had this from 1, and then the problem would have been trivial. Like if you had this thing for k equals to 1, then you would have a complete cycle of equalities, and then it was trivial. But now it is like like now we will have to do one more step. Right? Did you get it? Like, okay, maybe I'll just give an example. So like so what you want to show that you want to show that this implies that t of all this t of n minus 1 comma 1 is equals to t of n minus 1 comma 2 is equals to t of n minus 1 p minus 1, right? You want to show that this implies this, and right now you have some like you have this inequalities, like some inequalities like this and this, and like right now you don't have this thing. You have to show that this implies this thing, right? Right now you have only like two terms are the same. So how do you go from this to this? Like how do you show that t of n minus 1 comma k is equals to t of n minus 1 comma k minus n for k equals to 2, 3, dot p? Why does this imply that t of n minus 1? In fact, I'll prove that this implies that t of n minus 1 0 is equals to t of n minus 1 is equals to t of n minus 1 comma p minus 1. Right? So what will use like what is that called? So like if you will like think about it, so suppose you have like the residues modulo p 0, 1, 2, 3, dot p minus 1 arranged on a graph, like, and so what this is saying here that for k is equals to 2 to p, like so 2 like t of t n minus 1 k comma 2 is equals to t of n minus 1 k 2 minus n, then this is equals to some 2 minus 2 minus 2n.
Can you wait for 2 minutes just to let me think about this?
Sure.
How this implies that, like that k of k n minus 1.
Yeah, sure.
I think we are just done because GCD of n comma p is equal to 1. So like if we just keep continuing the cycle.
Yes. Yeah. So like this is the point that you we would have been done right now if this inequality started from k equals to 1, because only then you would have been able to travel across all this. Okay, so like I will just like tell you like what's happening. So suppose P is 7 and N is 4, right? So you have the correspondence like K to K minus N for K is equals to 2
But
to
I think doesn't matter much because the cycle has basically two endpoints and one of those must be not equal to one. So we can increase the one which is like not equal to one.
wait, I didn't get what you're trying to say.
Like basically we want to form a cycle in a graph, right?
Yeah, like we want to show that the graph is connected. Like,
Yeah.
yeah,
So we start at any random point, say k equal to 2.
yeah.
We go for do we go to like 2 minus n.
Yeah, so like let's say we go away from 2 to 5 in this example.
Yeah, so at any point we basically have two endpoints in the path, right?
At any point, we have two endpoints in the path. Right?
Like we want to make the path a cycle, right? We want to return to the point we started in the.
We don't want to make it a cycle. We want to show that the graph is connected so that all of them turn out to be equal. Like, you have to show that like t of n. So basically, what we want to show is that suppose you have this graph like 1, 2, 3, 4, 5, 6, 7, and let's say you are connecting 2 to 5, then your like 5 will go to 5 minus 4, which is 1. Then okay,
Yeah, that's what I'm saying. After 5 goes to 1, you move 2 to somewhere. You connect like 2 is equal to k minus n for some k, right?
yeah. So let 2 will come from 6. Yeah.
Yeah. So like among like this 6 must return to 1.
Why? Why must 6 return to 1?
Oh, sorry. Like 6 will return to 1 only if we have covered all the another numbers. This can be proven because GCD of n comma p
Yeah,
is equal to 1. So we
yes,
are done.
yeah, exactly. You could have proved it if you had this thing starting from k equals to 1, like if you had this inequality for all of this. But now you have this starting from k equals to 2 to n. Like, do you get it? Like, like you have that one. Like if you had that, this was from k equals to 1 to 7, then you could have gone from 6 to 2 to this to 1, right? Like, but now you can't utilize the fact that let's say 1 is connected to minus 3. So if something lands on 4, you can't like so okay. So yeah, this you don't know about the existence of this.
Okay, I will give a much cleaner argument. Like we know that 1 and 1 plus n are connected.
You know that 1 and 1 plus n, sure, yes.
Then we know 1 plus n and 1 plus 2 n are connected.
What if 1 plus n turns out to be 1?
Yeah,
Okay,
yeah,
so it's
that's what I'm saying. It can never be 1 because GCD of p comma like 1 plus if suppose 1 plus
oh,
kn is
okay.
equal to 1.
Oh, yeah. Yeah. That's the correct argument. Yes. I got it. Like you're saying that this sequence can never be 1 because like 1 plus Sn can never be 1 modulo p for s less than p
Yeah.
because of only p minus and so both of these are less than p and p is a prime, so Sn can never be. Yeah. That's the yeah. So yeah, this was the so we have proved the second part as well. And so you can keep on going down like this, and but obviously like let's say for 2, like this thing obviously does not hold to like t of 2 comma 1 is not equal to t of 2 comma or whatever, like let's say for 3, like for 3 these three things are not equal, t of 3 comma 1 3 comma 2 and t of 3 comma 3, like, and if p is like say if p is greater than 3, then like, these are basically t like t of 3 comma 1 t of 3 comma 2, and so like for small cases it does not hold to, that's why it should not hold for any n less than p. So we are done with the reverse part also.
Sir, if possible, could you please also send the AOPS link of this problem?
Oh, okay. So this was from the American Mathematical Monthly. It was not on AOPS, if I remember correctly. I can tell you the wait. I can tell you the edition from which it is. There. It was from some recent American Mathematics. I will send it on Discord. Like from like a friend gave it to me.
Okay.
Yeah. Send like the name of like the send. I don't think this was on AOPS probably. Like this was from some this one only. I think we are out of time, so probably we can discuss the remaining problems. You can discuss the remaining problems on Discord whenever you guys get time. This one was the hardest problem in my opinion, and remaining ones are easier than this. Okay, so
Yeah, thanks for the class.
yeah, sure. Thanks for attending. You guys can leave, I guess. One. We'll ask Rowan to end the stream. You guys can leave, I think.
Thanks for the class.
Yeah, if you have any doubts, you can ask.
No, no.
Yeah, sure. Hi, the time is over, so I think you can end. Okay, yeah, hi. Yeah, the time is up, so you can end it. Yeah.